Hello and welcome to our second lab on electric fields. Today we're going to be examining the relationship between electric field and distance, and also voltage and distance. And we're going to look at a couple of equations that help sort of describe the strength of the electric field. One says that the electric field is equal to KQ over R squared. And sort of to define terms here, our electric field is equal to K, this is a constant, it's equal to 8.99 times 10 to the ninth newtons meters squared per coulomb squared. Q here is the value of your test charge. This is the charge that's creating the electric field. And R is the distance, a straight line distance between the point where you're measuring the field to Q, your test charge. Now we know that the electric field is simply the change in voltage over the change in distance. And so the steepness of this gradient, this rate here, V over R, will give you the electric field. So a large voltage over a small change in distance indicates a large electric field. And so because of this, we can say that our voltage at any point is equal to KQ over R. And the difference between voltage here in the electric field is the R squared here in the electric field and the R down here in voltage. And so if you were to predict the dependency, the distance dependency of the electric field, you would say it varies with the inverse square of the distance. If you were to predict the distance dependence of the voltage, you would say that it varies with the inverse of the voltage. One more thing about electric field and voltage. The electric field is a vector quantity. And so this equation sort of describes the magnitude of the electric field. The way to determine the direction of the electric field, which you must, because it's a vector quantity, is to use the simple rule that the electric field will always point away from a positive point charge and toward a negative point charge. Now this gets a little more complicated when you have multiple charges together, and we have to use a method called the superposition method, all right, to determine the electric field. We have a direction due to one charge and a magnitude, maybe a magnitude and direction due to another charge, and we have to sum up those two different vectors using vector addition. Voltages, however, are scalars. And so being a scalar quantity, if you have two voltages due to two different charges, you don't need to sum those up using vector addition. You can just take the arithmetic sum of those two voltages, and that should give you the value of your total voltage superimposed by both, or however many, charges that you have distributed across your test area. Let's take a look at the simulator that we're going to be using to sort of describe these relationships. Our simulator is on the PHET website. You'll link to it. And as you can see here on the screen, we have some choices. Up in the top right, where my mouse is, there are some +1 nanocoulomb charges. And when I bring one down into the test area, you see that now on this voltage probe, I'm reading a voltage, and this voltage increases as I get closer to the point charge. And at any point along here, I can plot a line of equal potential. So this is similar to the ones you plotted by hand in the first electric fields lab. So this line of equal potential that I can plot anywhere, I can make multiple plots, and it'll show me the voltages. If I click show numbers, it'll show me the voltage level of each line. Now in here also I can check the show E field. And you see that it puts electric field lines, these are going away from the positive point charge, and their level of transparency indicates their strength. So a solid line, a solid arrow is more strong than a transparent arrow. And you see that the rules are obeyed in that these electric field lines cross the equal potential lines at right angles. And the arrow indicates the direction. Now I can also drag one of these orange electric field sensors onto the screen. This electric field sensor, if I move it to this 7.9 volt equal potential line, it shows me that there is an electric field here pointing away from the point charge of 7 volts per meter at an angle of 68.1 degrees down from the positive x horizontal. And so anywhere I move that along the equal potential line, it's going to have roughly the same electric field, just in a different direction. Another feature of this simulation is the grid. If I show the grid, you see that every dark separator there is a distance of ½ of a meter, and the smaller separators indicate a distance of 10 centimeters each. So down here in the lower left, you see this is 1 meter in the legend here in the lower left. So using this grid, I can determine the distance between any 2 points on the grid, and therefore I can use my equations for determining the value of the electric field and the value of the voltage at any point due to this positive charge. Now if I get rid of the charge, I can bring in other charges here and make any kind of distribution that I want and plot my electric field line around it, and it's going to, I'm going to get various values. So this is something that you're going to be able to play around with. In addition, we're also going to hopefully plot the distance dependence of the electric field and of the voltages within this grid area.